Okay, good. Before I begin talking about 21 centimeter cosmology, there's going to be, I imagine, some press release on this subject, but the Large Millimeter Telescope, 100 kilometers east of Puebla, has had its first light, and we had some small involvement in this development. We provided a receiver allowing them to make tests in a very simple way. So anyway, it's M42, seen at 45 gigahertz with a 50-meter active surface telescope. You see, this is a normal human-sized building here. So you see how big this thing really is. All dishes look alike, so you don't get quite an idea of the scale until you understand that it's 50 meters across. So this will eventually be outfitted with millimeter and sub-millimeter bolometer arrays. Great. And so, for example, you've seen wonderful data from Scuba. The gain for every galaxy, Scuba galaxy with a telescope like this will be 10 times as large. So this is going to do some very exciting work. Anyway, that's quite exciting, and I was happy to say that the receiver that was used for this commissioning is the same receiver that was used for the commissioning of Python and Viper at the South Pole 15 years ago. So it was sitting in our lab unused, and we provided it to Enable. Anyway, that's exciting to me. Okay, so I'm going to talk about 21 centimeter cosmology, and I have to focus because the subject is so big. I only have an hour. I'm going to talk about intensity mapping, and I'm going to show you data that show that the foregrounds, the big problem with 21 centimeter cosmology is the rule of the foregrounds. We're doing a very good job of that now. And so I'm going to focus on showing you the data and how we are removing the foregrounds in actual data. So we're doing this mostly at GBT. We're going to start a project next month at Arecibo. And then we feel we'll need our own private telescope quite soon to do better at this. And we have a telescope designed based on cylindrical reflectors, the cylindrical radio telescope. And this is a prototype for it that we've built at a steel mill near the campus in Carnegie Mellon. So this is our private little telescope, the prototype in Pittsburgh. Here's some references. These are quite general and easy to read papers, the first three. Those are white papers for the Decadal Survey. And this paper is a review of the experimental situation. It's now a little over a year old, so it's already out of date. And then I particularly like this paper by Chris Hirata on the physics of the Wuerthausen field effect. This is how 21 centimeter, the 21 centimeter line gets coupled to the kinetic temperature of the gas. It's subtle physics. It's very robust. I think it's quite solid, but if you want to think a little bit about the subtle atomic physics here, this is a good paper to read. So there's some references. I'll go through very briefly the cosmic history of neutral gas. Cosmic history of neutral gas. This could be an entire hour lecture, but I'll go through it very quickly. We're going to focus on low redshifts. That's where I'm working right now most aggressively. We intend to do a baryon oscillation experiment with 21 centimeter intensity mapping. That's a dark energy test. I'll explain what intensity mapping is and why it's useful. The GBT results that were published a few months ago in Nature, and then some data from GBT since then, and then I'll start talking about the cylinder telescope. Okay, well, here's on one slide the history of the evolution of neutral gas. So at redshift 1000, the universe first becomes neutral, and the cosmic background is released. Before this time, the acoustic oscillations are oscillating in the combined photon baryon plasma, oscillating in the dark matter potential wells, and creating the baryon acoustic oscillations imprint in the matter and the acoustic oscillation features in the cosmic background. Now, then this sort of grayish stuff is the neutral gas, and the gas is primarily neutral until about redshift 10 or so, when it gets reionized by UV sources. Right, so of course some stars don't take very long to form, so some stars are likely forming very early. This is when they really get going, when sub-galaxies are collecting, and the Strömgren cells are percolating, and the mean free path is increasing dramatically, so that each star can now impinge its light on the smaller surface area that's remaining. So this is a rather abrupt transition. This is the reionization of the universe here by UV sources. But there have been UV sources earlier. So, and it takes only a little trace of UV to connect the 21 centimeter spin temperature to the kinetic temperature of the gas. Okay. So, all right, so during this period, well, I'll get to that in a second. It's possible to look at the growth of linear structure. The signal will be linear in the density, so one can study the growth of linear structure studying gravitation and primordial structure during this era. Here you're studying ionization fronts, the process of ionization of the universe. Here the signal is expected to be its biggest. I'll show you that in a second. And then even after the cells have percolated and the universe is largely ionized, gas remains. So a column density of 10 to the 20 per square centimeter stops UV radiation. And so if objects with that column density and higher can survive against the uniform UV, and they're around today. Today we have gas in the disks of spiral galaxies even still. But today, omega H1 is about 10 to the minus 4, 5 times 10 to the minus 4. And here, of course, it's 3%. 75% of the gases of the baryons are hydrogen. Okay, so there are a wide variety of telescopes proposed and under construction, and they're designed for various redshift ranges. At low redshifts, we've used the Green Bank telescope. We've proposed our own telescope. We're going to use Arecibo. Custom-built telescopes are popular in this range. LOFAR is the most expensive one, probably the one that will do quite well soon in the next couple of years, but there's also MWA and paper. I'm part of an effort at the Giant Meter Wave Radio Telescope. I helped design this one in China, which has had its ups and downs financially and management-wise. If you want to go to this high redshift, you probably have to go to space. Or I think it may be possible to do some of this from Antarctica. And right. So, but this is far in the future. This is decades away. Okay, so here's sky structure plotted as delta T in millikelvin versus redshift. So this big peak. Let me just go ahead and put the physics on top of this. So this big peak is the large-scale structure seen in absorption, and the gas during this period is cooler than the cosmic background. So I forgot to say that. After recombination and the fluids decouple, the photons are relativistic and the atoms are not. And so as the universe expands, the atoms cool faster than the photons. So the gas becomes colder than the cosmic background. And so a dense region ends up absorbing cosmic background, and it looks like a cold spot on the sky. So that's true here. Then the reionization happens, and it's quite complicated, but makes a bigger feature. Maybe 10, 20 millikelvin. Some people think this could be 100 millikelvin. There are models in which that's 100 millikelvin signal. That depends on whether the universe gets reheated before it's reionized. Reheating requires X-ray flux. Reionization requires UV flux. One really doesn't know at redshift 10 what the X-ray flux is. It's anybody's guess whether the universe was cold before reionization or warm. Anyway, then we go to the more familiar range of low redshifts, and large-scale structure starts to grow eventually non-linearly. And I've plotted on here the synchrotron spectrum, the line just representing the slope of the synchrotron spectrum, to show you, for example, how challenging this is. I would have to extend it up to here to show you how challenging that is. Against the foregrounds. That's the spectrum of the foregrounds. But the EOR signal is considered to be the thing that will be found first. But if you look here at low redshifts, we actually have some chance here to see at various spatial scales, each of these lines is a different spatial scale, the structure at low redshifts as well, because the foregrounds are weaker. And that's what we've succeeded in doing.
So how much do you scale the spectrum synchrotron then? You're misleading people by just showing the plot.
I am misleading people by showing the plot. Okay, so the brightness of the galaxy glow, I'll show you, I'll say more about it in a second.
There's about a factor of 1,000.
Depends how you calculate it, but yes, yeah, 1,000, I would say it's a fair number would be 1,000. Okay, so people are excited, the theorists particularly are excited about 21 centimeter because it's three-dimensional. You know, we have wonderful cosmic background experiments mapping the sky, thousands of L modes, and we have this beautiful image with millions of pixels across the sky, up to L of several thousand, right? But it is only a surface. And the 21 centimeter information is three-dimensional. It's a line, and each frequency is telling you what the redshift is. And so the volume available is tremendous. And this is what's gotten people excited. So here, for example, is the volume of the Sloan Digital Sky Survey, this little red region. And the experiment we're proposing covers this volume. Okay, that's our CRT experiment. And of course, this is a two-dimensional representation of what's actually three-dimensional. So, you know, it's more volume than you see. The EUR region is this shell, right? And ultimately, if you get out to redshift 50, you'll be doing this volume. So there's tremendous statistical power in all the information that's available from this three-dimensional problem. Now I'm going to start talking about real data. This is a spectrum taken with the Parkes telescope. Here's a picture of Parkes. This was in a movie, The Dish. I don't know if some movie, The Dish. It's a charming movie. Probably a little hard to find now, but it's fun. It's about Apollo 11. Anyway, this is a signal. There's a spatial subtraction on the sky and also a spectral flattening of the baseline here. And then you can see this line standing out. Beautiful rectangular structure of a nearby galaxy seen with Parkes. This is the Milky Way. This is the redshift frequency, 1420.4. And the spatial subtraction has not worked perfectly, and there's a little artifact of the Milky Way here. But anyway, that's how you find a galaxy with Parkes. Now you have to set some threshold that eliminates the noise to put that galaxy in your catalog. And usually you'll use 5 sigma cut for catalog, right? So there's some 5 sigma cut to put that in catalog. Now if I take strips of frequency, I can map the sky in each redshift range. So just detecting the galaxy, you're automatically getting the redshift, right? Okay. Now I can map the sky in various ranges of frequency, and that's what this shows. So this is the VLA, New Mexico, and it individually pointed at all these Virgo galaxies and mapped them individually. And those are 21 centimeter images of Virgo galaxies. And they've been put in 4 groups and color-coded by redshift. Just sort of coarse grouping by redshift, that's what the colors are. Now, these look like galaxies, basically, but I would ask the audience to tell me what's different between these and pictures of optical galaxies. It's a quiz now. Do those look like optical galaxies? You don't get to. George doesn't get to say. Anybody want to tell me how those look different from optical galaxies? Donuts. They lack the bright core. That's the brightest feature of an optical galaxy is this huge luminosity at the core, right? They're singular in the center practically, right? Very, very bright in the center. That's missing in 21 centimeter. Why is that? Well, 2 reasons for that. First of all, there's a lot of UV flux there, ionizing the 21 centimeter, and also the gas may have been depleted to make all those stars. So it's the suburbs of spiral galaxies that are 21 centimeter bright. Now, this was in a movie too, so next quiz. What movie? Contact. Yeah. Okay, now one can do cosmology, and so now one is just finding the galaxies, doing the 5 sigma cut, putting them on a plot, pie chart across the sky. It's like the CFA survey. Now, this doesn't go out very far. So this is taken with Arecibo. Arecibo is the world's largest single-dish radio telescope so far. Until the one in China is done. And but it only goes out to redshift 0.1 here because this is quite challenging because of the strength of the 21 centimeter signal base compared to the size of the telescope. This structure lines up very well with the CFA survey, even though 70% of these galaxies are not in the CFA survey. In other words, it's not the same objects you're looking at. Most of the dim ones here are low surface brightness galaxies. They don't make it into the CFA survey. And yet the structure lines up. It's the same large-scale structure, but it's seen with different populations.
This is then the distribution of the neutral hydrogen?
This is hydrogen. This is 21 centimeter emission used to make this gas.
And this map says the distribution of neutral hydrogen.
It is the distribution of neutral hydrogen peaks.
Yeah.
Right. Yeah. Yeah? Okay. Let's see. Oh, by the way, this is in a movie, which was GoldenEye, right? Tonight's the way we want to build a big telescope. We want to get ourselves in the movies, maybe get an Oscar. Good. All right, so we're looking for baryon acoustic oscillations. I won't spend much time on this. There are other talks about acoustic oscillations. These are the acoustic peaks in the cosmic background. They leave an imprint in the matter structure, which then grows by linear growth to form structures that can be seen today. But that's by Fourier analyzing one of those dot diagrams that I just showed you, the Sloan Digital Sky Survey, to find these baryon wiggles. These are the baryon wiggles. Same thing as the acoustic peaks in the CMB, but in the matter structure today. Okay. Now, I won't go through how this is a dark energy test because there are other talks about baryon oscillations. Interesting for us is that it's a spherical shell we're looking for. A matter density in the early universe creates an acoustic wave which goes out spherically, and at 380,000 years that is frozen into the matter structure. And so we can look for it in 3 dimensions, this 3-dimensional spherical correlation. And the 3-dimensional structure will help distinguish this from foregrounds. It's very important for the point of view of removing foregrounds. Yeah. Okay, so now I'm going to talk about intensity mapping. And the first paper I found on this is by Shivsethi in 2005. Our paper on it is 2008. And at the same time, Logan Wyeth wrote a similar paper talking about some higher redshifts. So what's the idea? I'm just going to illustrate it here with this beautiful Hubble image of the Sombrero Galaxy, and we're going to decide how good the projector is now. Yeah, this projector is so-so. Okay, so now I ask the audience to find a star. And am I wrong, right? Right over here, there's a star, right? How do you know it's a star? I mean, that's a blobby galaxy. It's actually, spilling over into pixels. It's so bright. It's got this thin line on it, which is, because the brightness is so sharp on the sky, the scattering from the spreader that holds the secondary shows up in the image. And now you can, it's not, again, the projector's not so good, but on my screen, I can tell you that this has also got a thin cross across it, so that's a star too, right? There are actually about 5 stars in the image that you can identify. Of course, I'm cheating a little bit with the semantics because it isn't that all stars, right? We don't call it stars, we call it surface brightness because, of course, it comes from stars. But when we don't resolve the stars, when we have 1,000 per pixel as in this image, we just consider the surface brightness. Of course, CMB observers are very used to surface brightness, right? Now, what we want to do is do that surface brightness study with large pixels in 3 dimensions using the 21 centimeter line. It's 3-dimensional specific intensity mapping using the line, okay? So I'll just go back here, a couple of slides here to that image. So we will take largest pixels, so maybe this size, like that, in 3D, and we'll take all of the flux that comes from that pixel. Now we're not doing the 5 sigma cut anymore. You realize how damaging a 5 sigma cut is, right? You're saying, I need a real outlier here before I'm going to put it in my catalog. It throws away 99% of the flux to do that, right? You don't need to do that. Just take the flux. That's the idea of intensity mapping. Okay? We think we need a telescope to reach redshift 1 to 3, which is what we want to do, to take the square kilometer array if you wanted to find every galaxy, if you wanted to do this redshift survey with a cut. If you use intensity mapping, we only need 1% of the area. Very powerful. Okay, so we decided to try this at the Green Bank Telescope in West Virginia. We decided to try it on a field where we knew the answer. That's the Deep 2 redshift survey field. We've now done Cosmos and working on Wiggles fields as well. And here's our scan across the sky. So this is now in co-moving space, 3 projections in co-moving space. In the red tracks here are 6 scans across in right ascension. And the green dots are the Deep 2 galaxy positions in 3D. There are roughly 10,000 galaxies here for us to use. And because we know which position should be bright in 21 centimeter, we can do a stacking experiment. Get the signal even though it's weak. Okay. Now we ended up averaging 3 because the beam size is taller than our scan. Where we're sampling, we ended up averaging the top 3 and the bottom 3 in two groups. And then we get spectra. So here's a spectrum for the sky. This is just to show you the sort of thing we actually have to deal with. So these are television stations. Okay. So any real cosmological signal will go much thinner than the line, right? So these are thousands or billions of times brighter than the signal line. So you've got to get rid of television stations first. We can watch Pittsburgh television from the Green Bay telescope, even though it's 200 miles away. Anyway, after we move the worst of the RFI, here's what our data looks like. So this is across the sky, 2 sections actually, strips across the sky. And this is frequency, presented here as co-moving distance. And the stripes in the image are extragalactic radio sources. They're present at all frequencies, they're continuum sources, synchrotron sources, so they extend across the image this way. And the vertical stripes are places where we've removed data because of radio interference. So this is all cut up. Now, we need to remove that synchrotron emission for the foregrounds, which is this 1,000 times brighter structure on the sky that we want. And we do that with an SVD technique. And ask me later about how it works. It allows this cut up data to be analyzed very conveniently. Here's our foreground removed image. And the little patches here are getting down to the level to see 21 centimeter glow. Not quite, but it's close. This is the optical data analyzed in the same way. And so if we have a 21 centimeter signal, these two should look similar. So I'll let you stare at them for a second and decide if those two look alike. Do things line up? They do. And you know that because if you slide them away from it, if you multiply 2 together, take the variance, and then slide them apart from each other, the variance goes away. So excess variance when they're aligned, it goes away when they're not. That's a correlation. And here's the correlation function versus frequency. And so we're sliding in frequency. And here are the data points. This is that excess variance going away as we separate in frequency the two. So this is a cross correlation between deep 2 galaxies. 21 centimeter glow. And these are various jackknife tests and various null tests scrambling one of the 2 redshift sets, and several of them just to show we get you a 0 when you do a set of these null tests. This is a model. This is roughly R to the minus 2 correlation function, and then spreading due to velocity dispersion in redshift. That's a sort of Gaussian shape. Yeah, so we're claiming that's a detection, and it got accepted by nature, so it must be right. This is more 21 centimeter gas than has ever been detected by human history. This is 2 times 10 to the 14 solar masses of H1, and detected at redshift 0.8. Omega H1 is about 5 times 10 to the minus 4, and it looks like we're getting some mileage out of this intensity mapping idea. Able to handle the foregrounds. Next step is to try to get a signal without the optical redshifts, just the 21 centimeter data now, radio data. So what we're doing now is mapping the sky using cross-linked mapping like the ACT telescope does. So this is done with GBT, and we scan the sky this way, and we scan the sky this way. This is when it's rising, and this is when it's setting, and we're scanning horizontally. Then we create an optical cross-linked map, ACT, and these are the bright radio sources here, and then this is what we get after we subtract out the bright radio sources. What we do is we take all that's common in frequency in this image, and we subtract it away. Any smooth function of frequency that's common in that image, minimizing the variance of the things that are common in frequency. We get that, and then this is an enhanced contrast version of that. And this is now down to within a factor 2 of the expected 21 centimeter signal. You can see we still have some artifacts and incomplete coverage. We're not quite done yet. This is not ready for publication. But we're getting close. So we're now within a factor 2 of getting rid of this foreground. So the foregrounds are challenging, and the takeaway message here is we're handling them anyway. Because of the smoothness and frequency, we're able to remove the foregrounds. All right. We're also doing some work at Arecibo. Arecibo is much worse for RFI than Green Bank. From the feed structure up on the platform in Arecibo, you can see 6 television towers on the horizon. It's truly scary. And this is, we recorded the spectrum ourselves. We took our own spectrum analyzer. But there is this clean band right here, around 800 megahertz. So we have a filter for that band. It's a 7-stage cavity filter, which we have to put in front of the LNA. And we built our own feed for Arecibo. And this will be used full-time on Arecibo in parallel to all other observations. So this is going up next month, and we'll be mapping the sky continuously. Arecibo is mostly used for the alfalfa survey, or alpha survey, and that does strips of constant declination, so we'll be doing strips offset from them at constant declination as well. And we get thousands of hours per year. We can only get a few hundred hours a year on GBT. This has got a higher system temperature, and we don't get to do this cross-link mapping. But more data is always good. We use some tricks here. We filled the first Fresnel zone of the sphere with the beam of our telescope, and then we dialed the position of the feed off of the geometric focus to optimize the phase errors of the first Fresnel zone. Maybe that's too much technical detail for the non-experimentalists. But it works pretty well. We think we're going to get a 10 arc minute beam. We'll see when we actually measure it. But a 10 arc minute beam and thousands of hours a year, that's kind of exciting. Okay, now, even that is not good enough to do a good BAO experiment. We need all sky coverage. We need, basically you can work out how many receivers you need. And the answer is you need at least 1,000 receivers running for a year to do this job right. You're not going to put that on GBT, you're not going to put that in Arecibo, you need your own telescope, and so we've set out to design the simplest telescope we can that can put 1,000 receivers on the air and cover the entire sky, and this is this cylinder telescope. So we collect the radiation with cylindrical troughs onto a line feed here, and so there are antennas sampling the arriving wave along that line. It's assembled and reassembled in a computer. If I can explain basically how this works, if I have a wave coming down straight from above, it arrives in phase at all points along the line. So I just add it up in phase, no delays. If the wave is coming from an inclined angle, a little bit south, this is the north direction, a little bit south, even by one wavelength along the length, it will now cancel in the sun. Right? So I have a sync function beam on the sky, very narrow, given by the diffraction of that length, diffraction width of the length. Now, if I want to look at that angle, all I have to do is put a phase factor from one signal to the next. Just delay it in the computer. And I can do those two things simultaneously. In fact, I can do a fan of beams simultaneously from north to south across the sky just by computation. Okay? So I just let the Earth turn then, and I can map the entire sky every day. No moving parts. You like it? I think it's kind of cool. So it has no moving parts, very simple, very cheap, accommodates 1,000 receivers, and sees the whole sky every day. It's just perfect for BAO, right? Okay, so that's our idea, and there are some specs. We have a large collaboration that's working on this, and this is the roster. And people have been working now 4 or 5 years on this, developing electronics, modeling, simulating. We built a prototype, and here's some simulations. Nick Nedden and Dave McGinnis have worked hard on this, and John Seol have worked hard on this at Fermilab, and working independently, Reza Ansari and a group in France have done their own simulations. You have to have one of these figure of merit plots of W and W derivative with a tiny ellipse in order to get funded. So we make a very tiny ellipse. So our ellipse is as good as anybody else's ellipse. Don't believe anybody's ellipse.
fourth generation, not a third generation.
Well, it's only a $20 million project, it's got different systematics. I don't know what we need to be, but,
It's a question of what time you come on.
right.
Third generation is running
Yeah,
now, fourth
yeah,
generation.
You know, it's such an important measurement, it has to be done more than one way. That's the key argument. It doesn't have to be the best, although it's competitive with some of the best experiments. Okay, here are just pictures of what the BAO looks like on the sky, a redshift 0.1, 0.2, 0.3, it's going this way, 0.1, 0.2, 0.3. And eventually it gets to look like the CMB structure, but it's quite big on the sky at low redshifts. That's because it's a co-moving object, right? And when it's close, it's huge on the sky. Right? And so this is just a simulation of the removal of this. So this is now in K-space where you get the spherical shell, but the foregrounds are not a spherical shell in K-space. They're very concentrated at low K. The galaxy makes a low K structure on the sky, very extended. That means you can subtract it. And this has been run through a simulation of the whole cylinder telescope processing and just the most rudimentary simple cut, not a Wiener filter, just some rectangular cutout. And here are the, it's not working, but here's the VAO feature coming out. It's only really killed in the central square here. So one is going to get a very good VAO measurement despite the foregrounds, according to the simulations. Of course, there are other things to do here. This is a 500 megahertz to gigahertz radio telescope, very high throughput, very wide bandwidth. What can it do as well as cosmology? Pulsar searching. It's great for pulsar searching. It's great for studying magnetic fields. The polarizations of radio sources rotate due to magnetic fields at these frequencies substantially. So this is an ideal place to do rotation measure maps. You might search for aliens. I think a cylinder concept is an interesting idea for the next generation beyond LOFAR. That's called HIRA. So this could be a stepping stone or prototype for HIRA. And the key thing here is that what we're doing is advancing the revolution in radio astronomy that I make an analogy to the CCD revolution in astronomy. So astronomy's been revolutionized by imaging arrays. People used to do photometry with an aperture and a photomultiplier tube, right? And now there are gigapixel cameras. So what we're doing is going from the one receiver per dish regime of radio astronomy to the 1,000 receiver regime. And then we'll go to 10,000, 100,000, and so on. Here's our prototype. I'm getting a little short of time here, so maybe I'll go a little bit quickly. Now, we built two cylinders. These are 10 meters wide, 25 meters long, spaced by 25 meters. It's out in the, this was the railroad yard next to the big steel mill building at the LTV. Now no longer a steel mill. It's just a mile from campus in Pittsburgh. There's a little bit of Feedline instrumented. We didn't have the money to do the whole length, so we just did a little piece in the middle. And here's a bunch of students having a lot of fun. By the way, this is a lot of fun. You know, so we get to go around the world. We students build things and they work. It's low tech. It's a low tech telescope. You know, I built 47 millikelvin bolometers and put them on telescopes at the South Pole in 1988. So I know about high tech, but this is low tech, and I find it to be a lot of fun. Anyway, here's some dipoles picking up the signal. You can see there are antennas going this way. There are also antennas in the plane of the board for two polarizations. They're interleaved 0.7 lambda spacing. That is going to produce some grading artifacts on the sky. We knew that going in. It's just what we decided to test first. But there's an array of receivers. And, you know, all the RG6 coaxial cables and down converters and so on. Very simple. This is the active receiver amplifier element. That's made for a satellite downlink so you can watch your digital television on your dish network. That's what that's for. Costs a couple dollars. It has the best ones today have a temperature of about 25 Kelvin. So I can make a 25 Kelvin amplifier with a $2 part. Now, that's why this cylinder scheme is working now. So it was unpopular for a couple decades because cryogenic receivers allowed you a low system temperature, but you couldn't afford many of them. So you had to curve the dish in both dimensions to bring all the light to one expensive receiver. Now receivers are cheap. You can spread them out again. We don't want to spread them out in 2D because you still have to sample these signals, and that's the part that's still expensive. Here's our computer that does the sampling. The rack on the left has the sampling boards in it. The rack on the right is some more modern 8-core machines, which does the cross correlations. It's a PC array. It's really very simple, but it takes a while to make it all work. You're not going to be able to read much of this. So this is the structure of the correlator. Sampling system is the column on the left. We've proposed a 512 sampler system to NSF. Communication is, those are sampled, fed by optical fiber into the rack of computers. PCs put that all on gigabit networks, which get concentrated by switches into 10 gigabit networks, which go into GPUs. We haven't done that part yet. We've done the top 2/3 of this, but the GPU part we haven't done yet. It'll work. This is some of the sampling electronics that was at the telescope. It's been designed in France by our particle physics colleagues at LAL and CEA. Sampling boards sampling at 500 megasamples per second into FPGAs and then out to optical fiber. Yeah. Here are fringes. So now this is the signal, cross product the signal on one cylinder. This is one dipole on one cylinder, multiplied by one dipole on the other cylinder, watching the visibility, the product, the broadband product of those signals as signus A passes over. Okay, so the red curve is the model and the black is the actual data. So there are fringes from signus A that calibrates those receiver channels for you. This is the stability of the calibration. This is one day the 24th and the next day the 23rd, and this is a comparison of antenna-based versus baseline-based calibration. That's the red and the black, and then the difference of those between days is very stable. It's important for interferometers. We don't do any Walsh switching in this interferometer. We could, but we find at this point it's not necessary. It's not, so that's not necessary. And now I'm going to show you 21 centimeter images of the galaxy made with this prototype telescope. As I said, the spacing of the antennas is 0.7 lambda, so we do have grading lobes on the sky. So this little piece, this is a little piece of the galaxy. This is a narrow slice of frequency, 100 kilohertz. So this is a little piece of the galaxy globe, and this is an artifact of it, a copy of it, at grading order 1. So this is grading order 0 and this is grading order 1. Now one of the things we discovered in looking at the Pittsburgh data is that we know how to put this back on top of that. And the reason is the fringe rate for that object we know because of its declination. It goes over the telescope at a certain fringe rate. If it appears here in the image, it ought to have a different fringe rate because it's at a different declination. So by filtering for the fringe rate of this declination at that declination, we can find that object and put it back on top of that. We haven't done that yet, but it'll work. So we can do order sorting and remove the aliases, put them back where they should be. That's an important step for us because we had been thinking we had to pack the antennas in at half lambda spacing, and now we realize we don't. So we're very happy about that. Now this has had continually removed, so it's designed just to see 21 centimeter emission, but there are little artifacts of the continual removal. This is the sun. That is Cassiopeia. Yeah, Cassiopeia. And Cygnus A is someplace right in here. And now I'm going to step in frequency, and you're going to see the differential rotation of the galaxy here. So here we go. So this is right ascension and declination, but it's more than 24 hours. So you see the sun twice, so it's more than one scan across the sky. About 1 hour 30. Okay, so here we go. So that was the galaxy. I hope you liked it. Now look at this. So this is quite beautiful for us. We were kind of surprised to see this. That's just nothing but white noise. Here we are in Pittsburgh, Pennsylvania, with television transmitters all around. We're able to do low-noise radio astronomy, it turns out. We really didn't think we'd get this far. What this means is that we may be able to modify this Pittsburgh telescope to repeat the Sloan Digital Sky Survey in 21 centimeter, right in my backyard. I just am so jazzed. So. Anyway, yeah, so it's working very well. What's next for us? Well, we have funded now a larger version of this prototype in China. They're going to build 3 cylinders, a little bigger, and so that's not funded in China. So China has gotten the momentum as far as building things and gotten some funding. We have this 40-channel correlator that we can use in China, so already that's enough to do some interesting things. We've proposed the NSF of 512-channel correlator. Hopefully that'll be funded. But we have partners that are coming in with some money, and we may be able to build a good fraction of that anyway, even if we don't get the NSF funding. Our next goal is to map the large-scale structure using 21 centimeter intensity mapping at redshift 1. I think and also if we can, the BEO signal is about 10% of the large-scale structure signal. It's a little harder to get. But we'll look for velocity distortions in that data. That's interesting, I think, to people studying gravity. And we'll look for the BAO signal. Now, if we succeed at that, I think it's now just a matter of mass production to move on to the collecting area and number of receivers to build the full system. We need about $20 million to do the whole project. We're still looking for that money, and we're also still looking for a site. So we have not established where the site will be, and this depends somewhat on money. If someone comes in with the money, they can probably have it in their country. So right now, China is putting in the most money, and we've looked at 2 sites in China. The Baiqi radio telescope for solar observations, that's one site. I was there twice in the last year. Ulastai, where we built PAST, that's another possible place. The Kalahari site in South Africa. So all these places I managed to go to with my little antenna. So I've had the little world tour here. I go up with my spectrum analyzer antenna and measure spectrum. So this is a Mexican site, and this is Omar Lopez Cruz from Ineo. We went out to Zona del Silencio at the southern end of Chihuahua, and out in the Chihuahua Desert, quite desolate, not many people around. And this is, you don't recognize how good this is. This is very good. This is a very, very quiet site. Pittsburgh has lines that go way off the top of the chart here. So this is a satellite. This is the Orbcom satellite. This is the cell phone signal there. Your handset will not show a bar, I believe. I'm quite sure. I watched it and it died 10 kilometers before we got this far in. This is a very low level, but it's not, this is just a handheld portable testing setup. It's not of the sophistication of the testing of the SKA sites, so we haven't gotten to that level. But it's good enough for us to do our experiment. So I can't claim that this is as good as the SKA sites, but it's good enough for us. Next place we're going to go is Isla Guadalupe. It's 200 kilometers out in the ocean, 200 miles out in the ocean from here, way out west of Mexico. There are a few people there, but there are no television stations. So there's no cell phone tower. Yeah, okay. So those are places we've looked at. And I'm ready for conclusions here. So let's see. I think this 21 centimeter cosmology field is very promising. It's promising because even though the foregrounds are quite bright, the synchrotron spectrum allows them to be removed and it's heating at that removal. So that is really working, and I think 21 centimeter is really going to work out. The intensity mapping idea allows us to kick the galaxy addiction, right? The low redshift cosmologists are addicted to the galaxy. The galaxy is their fundamental particle. But we give up on galaxies and look at the sky glow without them, and intensity mapping, and that gives us much greater speed. We're reporting a detection of H1 emission at a record redshift, 0.8. The previous record was 0.4. We want to do a baryonic acoustic oscillation experiment with this telescope and many other things, large-scale structure and other types of radio astronomy. We're focusing on the redshift range 1 to 3 because that is where optical redshifts are very hard to acquire. The features, 8,000 angstrom feature has shifted into the infrared, and Lyman alpha has not yet shifted into the optical bands. And so above 3 is easier than 1 to 3. 1 to 3 is the hard spot. There is an oxygen 2 doublet that can be used. It's not impossible, but it's just much harder. So we're going to concentrate on the range that's hard for optical astronomy and try to do it with radio astronomy. I like cylinder telescopes. I think they're very fast and cheap. Ours is $100 a square meter. We built a prototype. We're getting data with it, and the next thing we're going to do is build a bigger one in China. That's it.
Are there any questions? Comments?
Can you say a little something about the very high redshift and the Antarctic approach?
Yeah, I have a couple slides about it. There it is. Okay, yeah. So, Antarctica. So, why can't you do very high redshift radio astronomy from the Earth? Well, first of all, of course, the foregrounds are very bright, and you're going to have that problem whether you're in space or on the ground, the bright foregrounds from synchrotron emission. So you're facing that issue. But you're facing another issue from the ground, and that is that the ionosphere is opaque at around 30 megahertz. That's where your shortwave radio allows you to hear the BBC all around the world, right? So that's 20 megahertz. But in that frequency range, which is the frequency range we're talking about, the ionosphere becomes opaque because of the total electron content. This is a measurement of the total electron content, but you notice the dark strip here at the bottom, where the sun is not shining, the ionosphere is not ionized as much. And the total electron content is very low, and that means that the plasma frequency drops. Whoops. Here we go. So it's a little hard to read. Let me just make it full screen. So this is using that GPS data of delays, the total electron content, which doesn't have very good modeling in Antarctica, by the way. They've modeled the transparency frequency of the ionosphere. 40 megahertz right below the sun. But if you look here on the plot, it's going down to 7 megahertz. Well, it's hard to see, but it goes down to below 7 megahertz. So if you stick to the polar regions and you operate in the winter, you may be able to see out, some people think as low as 3 megahertz. So that's the reason to go to Antarctica. You want to stay away from the auroral ring. Here's the auroral ring because the ionosphere is turbulent there. So you probably want to be inside the auroral ring. So that means this is Ellesmere Island.
There's
Is
also
Greenland?
radio noise, right?
What?
The aurora also produces radio noise.
It also produces radio noise, yeah. In Antarctica, this is McMurdo Sound and Ross Island's right there, and the dry valleys are over here. So I'd like to go to the dry valleys, give it a try. It would not be as good as the moon, but it's a lot cheaper.
So the issue is you can only cover a limited part of the sky, or else.
Only for a limited part of the sky. We take what you get. A very nice feature of this very low frequency is that the antenna doesn't have to be efficient. So we can make 25 Kelvin amplifiers, but the sky is 100,000 Kelvin at these frequencies. So if the antenna is inefficient, it's okay. Right? I can make a 1% efficient antenna, and that's just fine. So I can make little loop antennas like is in your handheld AM radio. And I can get sky brightness limited sensitivity anyway. Very, very simple systems.
Any other questions?
Nope.
So, thank you.